Hello and welcome to 10.4 Comparison Test. We start off with a comparison test for series to see whether the series converges or diverges. This first one is called a direct comparison test. In the direct comparison test, we compare one series to a series that we're familiar with, and the series that we're given in the problem, we usually have it be less than or greater than the series that we're familiar with. And then the rule follows that if the series that we're familiar with converges, then the given problem series also converges. If the series in the problem diverges, then the one we're familiar with also diverges. Okay, so let's take a look at some examples, see how this works. So we have a series here, summation 5 over 5n minus 1. So what we could do is kind of reduce this fraction by dividing everything by 5. Okay, so if we divide everything by 5, so this ends up giving us 1 over n minus 1 over 5. Okay, now in the big picture of things, this is going to be very close to 1 over n. In fact, this would be greater than 1 over n. Right, if we're looking at the term in the denominator n, it's only being subtracted 1/5. And what do we know about 1 over n? 1 over n is a divergent series. Right, if we had summation 1 over n. So therefore we could say that the series that we were looking at also diverges. By the direct comparison test. Okay, let's take a look at another one. The series 1 over n prime, I say 1 over n factorial. We have the series would look like this, the first few terms. Now, let's take a look at what this would look like. So if we look at the terms individually, we have 1 plus 1 over 1 factorial would be 1, plus 1 over 2 factorial, that would be 1 over 2, plus 1 over 3 factorial, that would be 1 over 6, so on and so forth. Now all the terms are positive, the terms are decreasing. Now what can we compare this to? Well, if we had something we compare it to, something that we're familiar with, we're looking at the terms, we could have a 1 plus 1 plus 1/2 plus, we could have 1/4 plus, and this would continue. Next term would be 1/8. Okay, and that would continue like that. So the series I'm thinking about would be if we had 1 plus summation of 1 over 2 to the n. Now the series 1 over 2 to the n, this would converge, right? In fact, we know what this would sum to, because this is a geometric series. Right, so if we had the 1 plus, now here, this was, our first term would be 1, so that goes on top. 1 minus, our common ratio would be 1/2. Okay, so that means our sum here would be 1 over 1/2, which would be 2. And so added to the 1 in the beginning, that would give us 3. So 3 would be an upper bound, okay, for the partial sums of 1 over n factorial. Okay, it doesn't mean that the series converges to 3. But because we know that 1 over 2 to the n converges, and we know that based off of our terms, 1 over n factorial is less than 1 over 2 to the n, this one converges, so therefore our series in our problem also converges by the direct comparison test. Okay, let's take a look at another problem. Okay, so we have a series here. Okay, starts off with 5, then the 2/3, then 1/7, 1, and then it continues like this. And then they give us a formula. That would be the formula. So now looking at the big picture of things, we could ignore the first 3 terms. Okay, the real action starts with the 4th term. So these 3 we could ignore. Now, if you look at the formula out here, the 2 to the n in the denominator, that will drive the direction of this series. Okay, so we compare to 1 over 2 to the n. So now we know that 1 over 2 to the n converges. It's a geometric series. And we know the terms of 1 over 2 to the n. It would be 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus continues on and on. And in every case, the term in this problem, in the problem series, is going to be less than the term, the corresponding term in the geometric series. Okay, so because we're comparing to 1 over 2 to the n, and that converges, we could say that the series in our problem also converges by the direct comparison test. Okay, let's take a look at another test. Okay, this test is known as the limit comparison test. So in a limit comparison test, we compare the problem series with something that is similar to it, something that we're familiar with. Okay, generally the problem series will be AN, and the one that we're familiar with will be BN. Okay, and then once we figure out our BN, we apply a limit as n approaches infinity of AN over BN. If that equals C and C is greater than 0, then we say that both series converge or diverge. Okay. If we apply the limit n equals 0 and Bn converges, then we say that An converges. If the limit gives us infinity and Bn diverges, then An also diverges. Okay, so let's take a look at some examples with the limit comparison test. This one is a very popular test, very popular set of problems with these. We will look at these following 3 problems. Okay, let's start with the top one. Okay, so they gave us the terms, they gave us what it could look like. If we expand the denominator, we end up with the current form at the end here. Okay, so here's our series, and we're trying to figure out, does the series converge or diverge? Okay, so let's take a look. So we'll set this as our AN. AN equals 2n plus 1 over n squared plus 2n plus 1. Now for the Bn, in order to get Bn, we look at our function here, our series function, and we look to see what this will behave like in the long run. We look at the numerator, we look at the denominator, we look at the leading terms, the dominant terms in both the numerator and the denominator. So for example, in the numerator, the dominant term would be the 2n. That'll be the driving force. In the denominator, the n squared will be the driving force. Okay, so we would have to look at 2n over n squared. Now we could reduce that. Right? We could reduce an n with an n. So we're left with 2 over n. Okay, let's keep it simple. So the comparison we'll make for Bn, we could compare 2 over n, but I'm going to keep it simple. We're going to compare it to 1 over n. Okay, now going into this, I know that the series with summation 1 over n, this is a p series, right, when the p is 1, and we know that this one diverges. Right, so we should all know that by now. Right, 1 over n diverges. So that's going to help us determine whether or not an also diverges. Okay, so let's do the limit comparison test. We will apply the limit as n approaches infinity of an over bn. Okay, so we have limit as n approaches infinity of 2n plus 1 over n squared plus 2n plus 1 divided by 1 over n. Okay, so I have 2n plus 1 over n squared plus 2n plus 1. Now, divided by 1 over n is the same as multiplying by the reciprocal of 1 over n. Okay, so I could multiply by n over 1. Okay, so now when I multiply by n over 1, I can multiply just distribute the n to the top. Right, so that would give me 2n squared plus n over n squared plus 2n plus 1. Okay, and I know how to take the limit of this. I can divide all my terms by n squared. Okay, and I see that I have 1 over n squared, so as n gets really large, that goes to 0. This would become 2 over n, so this would go to 0. This would become 1 over n, so this would go to 0. And so I'm left with 2 over 1, which will be 2. Okay, so we see that we know that the 1 over n diverges. Okay, and we have a limit here. The limit is 2. And since 2 is greater than 0, and our bn diverges, so therefore our an will also diverge. Okay, and this would be by the limit comparison test. Okay, let's take a look at another problem. Okay, we're given the first few terms, and then we're given the formula. Okay, so this is our an. Now, just by looking at this, when this n gets really large, this is going to behave like 1 over 2 to the n. Okay, so I'm going to set my bn to be 1 over 2 to the n. Now, right off the bat, we know 1 over 2 to the n. This is a geometric series, so it will converge. So now we're going to figure out whether or not an also converges. Okay, so let's do the limit as n approaches infinity of an over bn. So that would be 1 over 2 to the n minus 1 divided by 1 over 2 to the n, which means I have 1 over 2 to the n minus 1 times 2 to the n over 1. Right? If I divide by my fraction, I can multiply by its reciprocal. Okay, so that gives me limit as n approaches infinity. The 2 to the n will be on top, and then we have 2 to the n minus 1 on the bottom. Okay, so now we could divide everything by 2 to the n. So I have divided by 2 to the n, divide by 2 to the n, divide by 2 to the n. Okay, now my 1 over 2 to the n, that becomes 0. And that's 0. And then here on top and bottom I get 1 and 1. So I have a limit of 1. Okay, and 1 is greater than 0, which was that first condition in the limit comparison test. And because Bn converges, An also converges by the limit comparison test. Okay, let's take a look at another problem. So here we have the formula for our next series. So An equals, I'm just going to rewrite this. I have the leading term n ln of n plus 1 over n squared plus 5. Now to figure out my Bn, again I take my leading terms, right, the dominant terms in both top and bottom. Okay, and I would look to reduce it, ideally. Okay, so my n ln n over n squared, I can cancel an n with an n. So it gives me ln of n, natural log of n, over n. Okay. And ln of n is, it's greater than, this is going to be greater than 1 over n. So I could compare this to 1 over n. Okay, so Bn equals 1 over n. And one thing I know about 1 over n is that it diverges. Okay, so now we're going to try to see whether or not An also diverges. Okay, so we would take the limit as n goes to infinity of An over Bn. So that would be n ln of n plus 1 over n squared plus 5 divided by 1 over n. So that would be n ln of n plus 1 over n squared plus 5 times n over 1. Okay, so if we distribute the n, then we would have n squared ln of n plus n over n squared plus 5. So now we take the limit as n approaches infinity of n squared ln of n plus n over n squared plus 5. Okay, so as n goes to infinity, what happens here? Okay, so we would divide by n squared. So here we would have ln of n. This would go to 0. This would go to 0 over 1. And as n goes to infinity, this would go to infinity. Okay, so that therefore tells us that since this matches our third bullet in the limit comparison, if the limit is infinity and Bn diverges, which we know it does, 1 over n diverges, then An also diverges. Okay, let's do a couple more. So let's say we had summation n equals 1 to infinity of 3n cubed minus 2n squared plus 4 over n to the 5th minus n cubed plus 2. And we're trying to figure out if this series converges or diverges. Okay, so to start off with, this will be our an. Now to figure out our bn, we look at the leading terms. Right, so we have 3n cubed over n to the 5th. Now if we reduce this, we would have 3 over n squared. Right, so we could think of this as 3 times summation of 1 over n squared. Okay, so we could compare this to 1 over n squared. Okay, so let's say bn equals 1 over n squared. Okay, now we know that right off the bat, 1 over n squared converges. This is a p series, right? And p is greater than 1. Okay, so we're going to look at basically whether or not an also converges. Okay, so let's do our limit as n approaches infinity of an over bn. So we have 3n cubed minus 2n squared plus 4 over n to the 5th minus n cubed plus 2. Now we're going to divide by 1 over n squared. I'll go right to the multiplication step. Multiply by n squared over 1. Okay, distribute that n squared to our numerator. So we have limit as n approaches infinity of 3n to the 5th minus 2n to the 4th plus 4n squared all over n to the 5th minus n cubed plus 2. Okay, so we divide everything by n to the 5th. So n to the 5th, n to the 5th. Okay, so this will be bottom heavy, so this will go to 0. This will go to 0. 1 over n squared go to 0. 1 over n, this will go to 0. So we're left with these cancel, we're left with 3 over 1, which is 3. And this limit is greater than 0, and therefore because bn converges, an also converges by limit comparison test. Okay, let's do one more. we have summation n equals 1 to infinity of n times 2 to the n over 4n cubed plus 1. And again, we're trying to see if this series converges or diverges. Okay, so let's take a look at the top-heavy, the leading terms in both top and bottom. Okay, so now we know that this is our an. For our bn, let's take a look. We have n times 2 to the n over 4n cubed. Okay, we could cancel an n with an n. So we have 2 to the n over 4n squared. Okay, so now if we look at the top is exponential, the bottom is a quadratic. Okay, exponential will always outgain a quadratic in the long run. Okay, so because this is top heavy, this is going to diverge. Okay, so I'm going to set this 2n over 4n squared. That's going to be my bn. Okay, and we just explained that this one will diverge. So now all we're going to try to do is see if whether an also diverges. Okay, so we set the limit as n approaches infinity of an, which is n times 2 to the n over 4n cubed plus 1 divided by 2 to the n over 4n squared. Okay, so we have n times 2 to the n over 4n cubed plus 1 times, do the reciprocal of the b to the n, so 4n squared on top, 2 to the n on the bottom. Okay, right off the bat you can cancel some things, most notably the 2 to the n from top and bottom. Okay, so that means we're left with limit as n approaches infinity. N times 4n squared will be 4n cubed. On the bottom we have 4n cubed plus 1. And then when we take the limit, we can divide everything by n cubed. Okay, so this goes to 0. So we're left with 4 over 4, which gives us 1. And this is greater than 0. And so we could say that because bn diverges, an also diverges by the limit comparison theorem. Okay, any questions, just let me know, email me. That's it for the lesson. Have a good day, have a good night. We'll see you soon.